Hello everyone, welcome to my presentation. Today I'll be talking about canopy height variation in relation to topography and vegetation type at landscape level. We derive the canopy height information and the topography information from airborne lidar scanning. The spatial variation of maximum canopy height are key driver of many ecosystem processes like the dynamics of carbon sequestration. So the researchers are always very interested to know what creates the canopy height variation. The answer is pretty obvious, which is topography, at least at landscape scale. So the availability of high-resolution topographic data, possibly from the airborne lidar scanning, will enable us to quantify the effect of fine-scale topographic heterogeneity on the variation of canopy height at landscape scale. Here, we can see the schematic diagram of how the lidar scanning looks like and how we can derive the canopy height information as well as the ground elevation information from the airborne lidar scanning. So having such wonderful data, we are interested to know how topographic feature influence tree height, but we are also interested to know how the other features like canopy gap position and the neighborhood tree density influence tree height. In order to answer this question, the study was conducted in the central Japan, which is Kyoto City. Our study area is around 230 square kilometer, and most of the trees of our study area are evergreen conifers and also plantation, which is also made from the evergreen conifers. So around 80% of the vegetation of our study area represent evergreen conifer species. So here we can see how a airborne lidar scanning looks like. It basically creates a 3D image of the forest. So we can very quickly get the ground elevation information as the primary feature. But from the ground elevation information, we can get some other secondary information like slope, aspect, topographic wetness, and curvature. And we can also get some other secondary features from the canopy height too. Like we can detect where there is any canopy gap like this and detect the number of trees in the neighborhood. So in our study area, we detected at least 14 million trees. So we used that 500,000 points from that 14 million trees to see the relationship between the canopy height and elevation. We found that the highest trees were found in the middle of the elevation range, which is 500-meter in our study area. We also found that the tree that grows on the valleys are taller than the tree that grows on the ridges. The reason may be the tree that grows on the valleys are enjoying more water, nutrition, and protection from the wind than the tree that grows on the hill ridges. We also get a positive relationship between canopy height and the distance from the gap, which means that the tree that grows on the edges of the forest are shorter than the tree that grows in the middle of the stand. We also found the negative relationship between the canopy height and the number of trees in the neighborhood. We can see that the tree that grows in the high density are shorter than the tree that grows on the lower density. But the relationship is pretty prominent for the coniferous species, but the lines are flat and not as prominent as the conifers for the broadleaf species. So we put all the information that we have and put it in the multivariate models. We found that the machine learning algorithm like random forest explained the most, which explained the 40% variation of the canopy height. So we also saw the variable importance in the random forest model, and we found that the topographic features are one of the important, but in addition to topographic features, like other factor like neighborhood tree density and distance from the gap also shapes the canopy height variation. In addition to topographic heterogeneity, canopy gap position and neighboring tree density drives canopy height. However, including all the variables can only describe 40% of the canopy height variation. So other factors like the stand age and soil drive the canopy height variation at landscape scale. Our study is conducted in the temperate region, which is Japan, but studying in Japan enables us to see the possibility and the uses of this cutting-edge technology in other areas like the tropical areas where the forests are very inaccessible to. For example, here we can see how the lidar scanning image looks in the broadleaf forest too. So along with the conifers, it also can give some useful information about the broadleaf forest too. That's all for my presentation. I would like to invite you to ask questions if you have any. Thank you very much for listening.